Hey everyone, and welcome to today's video. Today we will be doing a register incrementing example. So essentially we will be counting from 0 to 255 and visually see the output on this bar graph. So looking at our schematic, we're using the PIC18F45K20. This is a 3.3 volt microcontroller. On pins RA6 and RA7 we've got external 20 MHz crystal connected via two 18 picofarad capacitors. On port C, we've got all 8 pins being used to output the LED display via a 15 ohm resistor. Now this display will draw around 3 volts and the port will output 3.3 volts on each pin. So that is the reason we're using a low value resistor. So this is just here for current limiting to protect the pins. And also we're using pin RE3, which is the master clear pin, and it's being pulled up to VDD. In that case it's 3.3 volts. Also, if you're using hardware, make sure you check the datasheet and don't forget to connect the VDD and VSS pins. Now that we've looked at our schematic, let's go to our programming environment. So we want to start a new project. So we go to File, New Project, Microchip Embedded, Application Project, click Next. The device we're using is the PIC18F45K20. We're going to use Proteus, so we're going to not select anything here. We click Next. We're using XC8 version 2.46. Click Next. I'm just going to call it T1. It's going to save it in the default location where MPLAB stores its projects. Make sure these are checked, set as main project, and open MCC on Finish. Click Finish. So just give it a moment to load up the environment. We're going to use MCC Classic content. Click here, click Next. So here we have our user interface loaded. So we can see a graphical view of the microcontroller. So in our case we've got the PDIP package. So the first thing we want to do is set up the system module. So we go here. We're using an external clock and it's 20 MHz. So the first thing we do is oscillator select, HS oscillator, system clock select, FOSC, and the external clock is 20 MHz. If you're using hardware, for example the PIC3, PIC4, make sure this is not checked. And that's all you need to do for this bit. We also want to set the pins of port C as outputs. So we go into the pin manager grid view, go to port C, and we just make sure that the GPIO output is locked like this. That's all you need to do here. You can double check that that's done. So all of port C is an output. There's nothing more to do in this interface. So all you do is click generate and there should be a message shortly saying successful. Generation complete. You can click MCC to exit the interface. So now we've got our default code layout. So at this point I will copy and paste my working code so we can go through it. So we can see we're including the necessary generated files from MCC. We can see there's 3 different ways of incrementing a port register. So let's go through option 1 first. So imagine this code for option 1. So essentially we define a variable, we call it A. We then load port C with value of A. So initially it will be 0, so all the LEDs would be off. We then come into this while one loop and we have a short delay function. We then have that variable A incrementing by 1, adding 1 to it, and then loading that value back into A. And then lat C is being loaded with A. So this is like the least inefficient way of incrementing that port register. Option 2. You can directly increment in code the variable A and load it into lat C. And because in this case we just want to visually see the register incrementing, option 3 is the most efficient way. So I just want to make you aware of one thing. In our application, it does not really matter whether we put this before or after the variable I, but in some applications it does, and I just want to explain the difference so you understand. So in our first case, let's say we initialize our code variable to I equals 0. We then execute this instruction, lat C equals I++. What is actually happening here is that the current value I is being output on lat C, in our case on the bar graph. Then the variable I is incremented by 1, making it I equals 1. But we do not see that output at this moment in time. We only see the previous value of I at this moment in time. Then when we return to our main code, so for example in our example we've got a delay, we return back to the statement, and essentially that newly generated value of I, which is 1, is output on lat C. We then have I incremented by 1, so I equals 2 now, and then that 2 would be shown on the next execution of the code. In our second case, which is more probably closer to what you're thinking the code works, if we have I equals 0 and we execute this instruction, lat C equals ++ I, what happens here is that at first the I variable is incremented by 1, and then that new value is shown on lat C. So if, in our example, if we had used it this way, we would not see that lat C equals 0 on our output on the bar graph. Hence why I've used this way. Hope that explains the difference between both of them. So by directly incrementing lat C, which is the most efficient way in this regard, you can see the register incrementing using one line of code to increment and another line to have the delay value. So the output on the simulation would be the same, so I'll just run it this once. So what we will see is incrementing from 0 to 255. When it gets to 255, the register will overflow and the sequence will begin again. So I have just sped up the simulation so we can see the end result, and as you can see we reach 255 and then the register overflows and we go back to incrementing from 1. That's it for today's video. Hope you find it useful. Source code and files can be found down below, and till the next one, goodbye.